All right, that's fine.
Wait, where'd she go?
Okay. Shh. All right, so I want you guys to listen first. All right, so basically the idea is, suppose we have this test tube, right? And we have a mixture of all these different molecules, right? And some molecules are really, really long, right? So let's say we have a few long ones, right? And they're all about this, these are all the same length. And then we have some really short ones, right? Right, so we have a mixture of these molecules. Some are long, some are short, right? And I want to separate them, right? So the purpose of gel electrophoresis is that we're going to separate molecules from a mixture, right? By passing it through a gel, right? So here's the gel. And again, I'm like the worst artist ever, so please don't get confused by how bad my drawing is, right? So basically, so here's this gel, okay? And that's what I gave you right here, right? This gel is made of agarose. Can you guys tell what agarose is? Huh?
Agar thing, sugar.
Who said sugar? Why?
OSC.
Because it's OSC. So this is a polysaccharide, right? And that's why we're actually using this. That's why we're doing this technique right now in this unit, right? Okay. So this gel is made of agarose, and if you zoomed in really small, you would notice that this gel, like let's say this is like maybe a side view of it, like not perspective or anything. But so if we're gonna like zoom in right here, basically it's like this sort of like network of like, it's like a sponge almost, right? So that it kind of like so only certain things. So it's not just like totally fluid, and that things can't just like pass through at whatever speed they like. This is actually kind of like a spongy material, so it's kind of like holding things back that are trying to pass through it. All right? Can we understand that?
Yes.
Okay. Another thing that I'm going to tell you about these particles is that they have a certain charge, right? So let's say like all these like long ones here, they're all like positively charged, right? And let's say all these little squiggly ones are negatively charged, right? So how could I separate them based on that? Where will the positive ones want to travel? Towards something that is negative, right? And where will the negative things want to travel? Towards something that is positive, all right? So what we're going to do is we're going to take this gel, we're going to put it in this like big bath, right? And cover it up. This bath and this water thing, this is called buffer, right? And it's an electrolyte, meaning it has ions in it, right? And ions conduct electricity. So this buffer, this like kind of liquid, is going to help the charge get carried across the gel, right? Look at your gels real quick, or you can look at mine up here. Where is the comb in relationship to the overall gel? Where is it? Is it on one end or in the other end? Where is it, Lita? It's right in the center, right? So my wells here, they're right in the center here, right? Okay. So, do you guys understand this process? So what's going to happen is now, I'm going to turn this on, right? I'm going to turn this, let's say this is the positive electrode down here, and this is the negative electrode down here. And these are connected to a power source, right? Okay, so when I turn this power source on, then this is going to be positively charged, and this is going to be negatively charged, because there's going to be a current running through this liquid, right? What if this buffer, this liquid that I put in there, was just distilled water, which means there's no ions, it's just plain old water? What's going to happen? It's not going to carry any sort of current, so it's not going to attract anything, right? So it's not going to work. So it has to be this special electrophoresis buffer that I have in right over there in that gallon jug, right? And so I turn this on, and let's say what I'm going to do is I'm going to put a sample. There are these little dyes, right? I'm going to take a sample of it, and I'm going to put it in this well, right? So I'm going to fill up the well, right? And suppose this sample is negatively charged, what's going to happen over the course of time? Where is it going to travel? If it's negatively charged, it's going to go toward the positive electrode, right? So this slowly, after a few minutes it might be here. After a few more minutes it might be here, right? After a few more minutes it might end up all the way over there. So it's getting closer and closer. It wants to go to the positive electrode, right? Are we all okay with that? All right, if something's negatively charged, suppose I put my next sample in here, right? There's another sample, and suppose this one goes this way. What does that mean that is in the sample? We know that the sample is what? Is positively charged. The molecules inside there are positively charged, so they're moving this way, right? So it separates, so one basis on which electrophoresis separates something is based on their charge, right? Suppose that all of these are all negatively charged in here, right? So they're not going to be separated by charge, but they're going to be separated by what instead? They're going to be separated by size instead, right? Do you think if there's all this gunk to go through, this is what the actual gel is made of, if there's all that gunk to go through, do you think smaller particles are going to go faster, or do you think larger particles are going to move faster? Smaller, right? So suppose I have a third sample that actually looks like, here's my third sample, I'm putting it in here, and it actually looks like this. It has 2 bars. What does that mean?
It's a larger sample. Broken up.
It means that there are 2 different sized molecules in this one. Some that are
Moving faster and some are slower.
Some that are moving faster and some that are moving slower, and that means these are
Smaller.
and these are
Bigger.
These are bigger, right? So it's taking them, they're getting dragged, and it takes longer for them to go through, right? What if I only have one band? What does that mean? That means that all the molecules in that, they're not mixed like this. They all just have the same exact, length. They're all the same, so they're all moving together at the same speed, right? But so if you see 2 bands, you know that the original one contained a mixture of different bands, right? All right, and if I said, suppose this one's traveling over here, traveled this much, right? And then this one over here traveled this much, right? What can we say? So we know that these particles are what charge again? Negative, and these particles are positive. But which ones are larger? The ones over here, because they traveled less, right? Because they are larger and heavier. All right, Lido?
If given enough time, could they both reach the end?
Yeah, and then they fall off the gel, and then it doesn't work. So you always have to stop the gel before they kind of go too far, right? Yeah.
Do you have 2 molecules in the same, the same whatever those boxes are? One's positive and one's negative.
Yeah. So what would that look like?
One's on one side and
Exactly.
one's on the right.
Exactly. So if I have a mixture, and then my result kind of looks like this, right? That means that how many different sized molecules were in this one to begin with? 2, right? Or how many different molecules? And they're both, one's positively charged and one's negatively charged. Exactly. That's good. That's a really good question. All right? So some of the dyes that I'm going to give you today. So each table is going to get a set of, how many dyes are 1, 2, 3, 4, 5, 6, right? There's 6 dyes. I think there are 5 of certain colors. And then there's 1 mystery mix